Hello everyone. Today we'll start the percentage composition of a compound. Start with percentage composition of a compound. Now, percentage composition means the relative amount of each element in a compound, right? In more simpler terms, it is the percentage of a one element in the formula of the compound. Now, how to calculate the percentage? Before calculation, the definition is the relative mass of each constituent element in 100 parts of it by mass in the compound. Now, how to calculate this? To calculate percentage composition, I repeat, percentage composition means the relative amount of each element in the 100 parts of the compound, in the 100 part of the compound, 100 parts of the compound, right? To calculate this percentage composition, first of all, we have to find molecular mass of the compound. Like here, I take the example of calcium nitrate. To find the molecular mass, we add the atomic masses of all the atoms of all elements present in this formula, calcium nitrate. So here is one calcium atom, two nitrate atom, N into 2, and 6 oxygen atom, 3 into 2, 6. So 6 oxygen atom, 6 times atomic mass of oxygen, 2 nitrogen, so 2 times atomic mass of nitrogen, and 1 calcium atom is there. Now, we will find the molecular mass of the calcium nitrate, which is 164 here. Now, percentage composition is in terms of all its elements. So, it is the relative amount of the element in the compound out of 100. The percentage composition of calcium, the mass of the calcium in the formula divided by molar mass into 100. So, mass of one atom is 40 U. So, we take 40 divided by 164 into 100, that is 24.39%. Then percentage of nitrogen. So nitrogen is 2 times 2 atomic mass. So 2 into atomic mass. So 14 into 2, 28. So we take mass of nitrogen in the compound is 28. So mass of nitrogen in the compound, in the chemical formula of the compound, 28 by 164. So into 100, it will be 17.04%. Next, percentage of oxygen. Now, oxygen, there are 6 atoms of oxygen in one molecule of calcium nitrate, and one calcium nitrate molecule has mass 164 U. So 6 oxygen atoms have mass 96 divided by 164 into 100. 58.54%. So this is how we can calculate the percentage composition of the compound in terms of different elements. Now, there is a numerical problem. This is how you will get the questions in the examination. So sodium is an essential constituent of our body. Calculate the percentage of sodium in breakfast cereal which has been advertised to contain 40 mg of sodium per 50 gram of cereal. So amount of cereal is given 50 gram total amount, and the sodium amount is also given, but the units are different. So keep in mind, whenever you are doing calculations, so take same units. So if it is not mentioned to give answer in which units, so you can take any gram or whatsoever you want to take milligram. So percentage composition in this case will be equal to mass of sodium, which is 40 milligram, and 40 into 10 to the minus 3 grams, and divided by total weight, 50 into 100.08% of sodium is present in 50 gram of cereal in breakfast cereal. Right. Next question is, P and Q are the two elements which form two compounds, two different compounds. One is P2Q3 formula and the other is of PQ2 molecules. Now, if 0.15 gram mole or 0.15 mole, so this is mole, not gram, mole of each weighs 15.9 gram and 9.3 gram respectively. What are the atomic masses of elements P and Q? So let here point, so mole are same for the two compounds, right? So 0.15 mole of first compound, first molecule is 15.9 gram, and the first second nine. So for the second compound, it is 9.3. So same moles. So moles, number of moles are equal to given mass upon molar mass. Now this mass is given, moles is given. We can find the molar mass from these two quantities. We can find the molar mass first of all, right? So the molar mass of P2Q2 will be 106 by putting in this formula 0.15, and given mass is 15.9 for this molecule, and the molar mass will be 106 gram per mole. And for the PQ2, the number of moles will be equal to given mass. Given mass is this time 9.3, and the molar mass will be equal to 62 grams. Now, from equation this 1 and 2, which we made after this, the molecular mass of P2Q3 is, if the atomic mass of P is A and the atomic mass of Q is B, then the formula P2Q3 will be equal to molecular mass 2 into A, 3 into B, 2A plus 3B. And for molecular mass of PQ2 is equal to atomic mass of P is A and atomic mass of Q is B, so it is 2QB. So this is molecular mass of PQ2 and this is molecular mass of P2Q3 if we assume the atomic mass of P is equal to A and atomic mass of Q is equal to B. Now, from these two equations, we can compare the molecular masses with these the two equations above, 1 and 2. So let it be this 106 is 3. So 106 is the mass of P2Q3. So it is equal to 2A plus 3B, and the other is A plus 2B. From these two equations, by equating them, we can find the variables B and A. So here is the value of B, it's equal to 18, and the value of A is 26. So it means Q atomic mass is 18 and atomic mass of P is 26 unified mass. Now the next topic is empirical formula and molecular formula. Now the compounds, the chemical compounds are always written in terms of a chemical formula. Now the chemical formula is the basic representation of any molecule. Now this representation is further on of two types. This chemical formula is further divided into two types. One is empirical formula, the other one is molecular formula, right? For example, the chemical formula of calcium carbonate is calcium CaCO3 and the sodium sulfate is Na2SO3. So basically chemical formula we know is giving the exact number of atoms of all the elements constituting the molecule of that compound. So what we are knowing till now is this: the chemical formula and molecular formula are same, and they are same in actual. But this chemical formula is of two types, right? One is empirical formula and the other one is molecular formula. The formula of compound which gives the simplest whole number ratio of atoms of various elements present in one molecule. Not the actual, but the simplest ratio, simplest whole number ratio. The simplest whole number ratio given in terms of empirical formula. And the formula which gives the actual number of atoms of various elements in one molecule is known as molecular formula. And in general, we are writing chemical formula and molecular formula same, but chemical formula is of two types: empirical formula and molecular formula. Empirical formula is giving simplest whole number ratio, and molecular formula is giving actual ratio of the atoms. Example: the formula of hydrogen peroxide here is H2O2. Now, in order to express this H2O2 in its empirical formula, the chemical formula in terms of empirical formula, we have to take out a common factor from this, first of all. Now, the common factor is 2. So, when we take common factor out of it, we get simplest whole number ratio 1:1. So, the empirical formula of hydrogen peroxide is HO. Similarly, for glucose, the molecular formula, the chemical formula is C6H12O6 molecular formula. In order to get empirical formula, a common factor 6 is taken out and we get CH2O. 1:2:1. Simplest whole number ratio of glucose, carbon, hydrogen, and oxygen 1:2:2. So the empirical formula of glucose will be CH2O. Now for writing the molecular formula, no need to take out any common factor. Actual ratio of atoms is considered. So molecular formula of hydrogen peroxide is H2O2 and for glucose it is C6H12O6. Now next is relation between empirical and molecular formula. In case of hydrogen peroxide, the molecular formula is twice the empirical formula, and in case of glucose it is 6 times the empirical formula. So it means there is a factor by which we can multiply the empirical formula to get molecular formula. So molecular formula is equal to n into empirical formula in general. Now empirical formula can be molecular formula can be obtained by multiplying the empirical formula with a common factor which is n for any compound. Here are the examples for benzene. Empirical formula is CH and the factor with which the empirical formula is multiplied is 6 and molecular formula is C6H6. For acetic acid, CH2O and 2 is the factor, CH3COOH. For glucose, CH2O is the empirical formula and the factor is 6. Now here, for the acetic acid and glucose, the empirical formula is same, but the factor with which we are multiplying is different. Ammonia, NH3, and same is the molecular formula, same as the empirical formula, the factor is 1. Copper sulfate, CuSO4, again the factor is 1. So here the empirical formula and the molecular formula are same, where the factor with which we are going to multiply empirical formula is 1. If it is 1, then the empirical formula and the molecular formula are same. Now next, how you people will get question in your paper, in your examination. So this is the topic, determination of empirical formula of a compound, and this includes both of the above topics, that is percentage composition as well as empirical formula and molecular formula. So here is an example to explain the determination of empirical formula of a compound. The example is a compound on analysis was found to contain carbon 34.6%, hydrogen 3.85%, oxygen 61.55%. Now we have to determine its empirical formula. Now how we can get empirical formula with the percentage composition of the compound? First of all, write all the constituent elements of the compound in a column like this. Then against each element, write its percentage composition in the compound. For example, for carbon, it is given 34.6, for hydrogen, it is given 3.85, and for oxygen, 61.55. Then, in the next column, write atomic masses of all the elements constituting the compound. This method, right? This is the first step. Now in second step, calculate the number of moles. So you are not given any specific amount of the compounds. So you will assume 100 as a total mass. So we are going to get relative uh, number of moles in by assuming 100 parts of the compound. So if each atom, so next we will find number of moles by assuming this as a mass out of 100, right? So this is the mass. So atomic mass is 12. So mass upon atomic mass will give you moles. So we are assuming total mass of the compound is 100. So relative number of moles of carbon is now 2.88. Similarly, for hydrogen, it is 3.85 mass upon molar mass. Sorry, atomic mass in this case. For oxygen, it is 61.55 upon 60. Right now, after finding number of moles, next step is to calculate molar ratio or atomic ratio. This will get by dividing the number of moles of each element with the lowest number of moles of the elements. So atomic ratio, number of atoms with respect to each other. So lowest number is 2.88. So this is 1, and in this case it will be 1.337, and in this case again it is 1.37. Now next step is to convert this atomic ratio into simplest whole number ratio. For doing so, we'll multiply all the atomic ratios with the same number. So 1.33 is equal to 4.3. So we'll get 4 by multiplying it with 3, right? So we'll multiply all the 3 atomic ratios with 3. And we'll get 1 carbon, hydrogen 4 atoms, and oxygen 4 atoms. What we did is we write all the elements constituting the compound. Then against each element we write percentage, then atomic masses of all the elements, then we'll calculate moles, means gram atoms, and then atomic ratio by dividing the moles with the smallest number of moles, then converting these atomic ratios into whole numbers. So this will give us the simplest whole number ratio of different atoms of all the elements constituting the compound. So here is carbon is 3, hydrogen 4, oxygen 4. So the empirical formula of the compound of this percentage of these elements in it is C3H4 oxygen 4. Next is chemical equation. Next topic is chemical equation. So brief representation of chemical reaction in terms of symbols and formula of the substances. For example, sodium carbonate plus hydrogen, sulfuric acid gives sodium sulfate, carbon dioxide, and water. Now, representation of what? So it is the representation of an actual reaction, not of all the hypothetical situations. It is the representation of actual reaction. The two or more substances reacting with each other can be expressed with the help of symbols and formulas. Is termed as chemical equation. Now, essentials of a chemical reaction. The first is it must represent an actual chemical reaction, like what I said earlier. It should represent an actual reaction. It must be balanced. So the total number of atoms of one type of element should be same on reactant side as well as on the product side. It should be molecular. It must obey the law of conservation of mass. That means the total mass of all the reactants should be equal to total mass of all the products. Now, what kind of information we'll get from the chemical equation? So chemical equation give us two type of informations. One is qualitative. Qualitative means which type of reactants, which reactant is taking part in the chemical reaction, and which type of products we are getting. So this is the qualitative information. The second is quantitative information. So this is important in aspect of this chapter. So quantitative aspect, quantity. So it gives actual number of reactant and product species taking part in the reaction. It tells relative mass of reactants and products, particularly in the reaction. Relative number of moles of reactant and products. It conveys volume of gases, reactants, and products. So quantitative relationship in terms of mass, in terms of mole, in terms of volume. What I write here is quantity, actual quantity of reactant and product molecules, moles, their volumes, right? So for example, the calcium carbonate, hydrogen chloride. So here gives calcium chloride, water, and carbon dioxide. So from this equation, what we are getting is one molecule of calcium carbonate reacting with two molecules of hydrogen chloride, giving one molecule of calcium chloride, one molecule of water, and one molecule of carbon dioxide. The second information, if we add and get the molar mass of calcium carbonate and all other species in this chemical equation, we are getting second information in terms of mass. 100 gram of calcium carbonate reacting with 73 gram of HCl, giving 111 gram of calcium chloride, 18 gram of water, and 32 gram of carbon dioxide. Now, the next information in terms of gases, we can get one mole of calcium carbonate is giving 22.4 liter of carbon dioxide. Why 22.4 liter? Because no condition is mentioned here. So if no condition is there, we assume it is reaction is going carried out at NTP, normal temperature and pressure. So 1 mole of calcium carbonate giving 22.4 liter of carbon dioxide. So this is mass and volume relationship. Now next is 1 mole of calcium carbonate giving 2 mole of HCl, 1 mole of calcium chloride, 1 mole of water, and 1 mole of CO2. Right. This is again 1 molecule of calcium carbonate reacts with 2 moles of HCl, giving 1 mole of calcium chloride, 1 mole of water, and this much of liter of CO2. So no reaction condition on the arrow. So we assume the reaction is carrying out at NTP. Now, the other informations we receive from a chemical reaction, or you can say these are the earlier limitations which are removed now by giving some additional inputs in the chemical equation. So physical states we get. Earlier it was not there, but now we are writing these: S for solid, AQ for solution in water, aqueous solution, and L for liquid, and G for gases. Concentration. So this word dilute, representing the dilute sulfuric acid in the reaction. And similarly, if we are using concentrated, we can write concentrated here. Now, condition of temperature, pressure, and catalyst. So here is an example of production of ammonia. So iron is used as catalyst. So 723 is the temperature and 600 atmosphere is the pressure. So we'll find the reaction conditions above and below the arrow. Then speed. Sometimes we write on the arrow, for example, for the ionic reactions, we generally write fast during representation of mechanisms of the reactions. So fast and slow words have also been mentioned. Heat change during a reaction. So sometimes the numerical figures are also a part of a chemical reaction. So here, like in this example, methane is burning, and a figure in terms of kilojoule is given on the product side with a positive sign. It means it is produced as a product. So heat is released during the reaction. Now in the second reaction, a value is given in negative. That means it is used. It is not produced, it is used. So energy is absorbed in this reaction. So if we want to write it in positive, so we can write it inside of reactants. Next, precipitation, solid formation, evolution of gas can also be understood from the arrows, like wherever it is precipitated, the downward arrow also, or PPT can be written. Reversible reactions, forward and backward sign. So we got the information that the particular reaction is reversible in nature. Now, problems based on this chemical equation, the stoichiometry problems. Now, first of all, what is this stoichiometry? So, stoichiometry is element measurements. Element measurement. Now, the chemical equation is giving quantitative relationship in terms of molecules, in terms of mass, in terms of moles, in terms of volume. So, between the reactants and the products. So, this quantitative relationship is known as stoichiometry. This quantitative relationship is known as stoichiometry. Right? Why it is stoichiometry? Or we can measuring the elements from it. We can calculate molecules, we can calculate mass, we can calculate moles, we can measure volume also with the help of a balanced chemical equation for the given concentration, for the given mass of the reactants or products. Now, the problems involving calculation are of three types basically. What you will get in your numericals is the problems are of three types. Whatever the problems, they can be categorized under three different types. The first type of problems can be mass relationship. The second is mass volume relationship, and the third one is volume relationship. Now, generally, there is a procedure to proceed for these proceed for the solution of these problems. And the general procedure is, first of all, you have to write a chemical equation for the reaction given in your problem, and that chemical equation must be balanced. The first step to solve stoichiometry problems is to write balanced chemical equation for the given change in the question. The second is select formula of the species whose weight or volumes either given or to be calculated. Okay. We have to target those species whose volume is to be calculated and whose is given. Next is write down atomic masses, molecular masses, volume, molar volumes, whatever is the given quantity in the question. We'll write those quantities like atomic masses, molecular masses, moles, or volumes for the selective species. Like for which species we have to calculate the volume, mass, moles, or molecules, and the other one is given, for which it is already given in the question. Now calculate the quantity desired by simple unitary method, by simple mathematical calculations. Now here is an example which is showing mass relationship. The question is, what mass of copper oxide will obtained by heating 12.32 gram of copper carbonate? Now, first step is to write the chemical equation of this reaction given in the question. So the reaction is on heating the copper oxide, on heating the copper carbonate, we are getting copper oxide. So copper carbonate on heating gives copper oxide and carbon dioxide. Now balance this, it is already balanced. Now the second step is to write what quantity is given. The copper carbonate mass is given. So we'll write copper carbonate mass, which is 12.35. We can write it here. And then third step is to calculate atomic or molecular masses of the different species under consideration. So under consideration is copper oxide and copper carbonate, because copper carbonate mass is given and copper oxide mass is to be calculated. So we calculate molar mass of these two species only. We have to do nothing with this carbon dioxide now, right? Now, from the equation, 23.5 gram giving copper 79.5 copper oxide. So this is copper oxide. This is copper oxide, right? Now 1 gram of copper carbonate gives 79.5 by 123.5. So 12.35 gives copper oxide 79.5. This is copper oxide 7.95 grams. So this is unitary method. Only thing is to write balanced chemical equation. Then which type of problem is we have to calculate mass. What mass? So we will write mass, molar mass of the species whose mass is given in the question, molar mass of that species, and molar mass of the species whose mass is to be calculated. Then we have simply equate. So this is copper oxide. So by mistake it is written as copper. Now problem based on mass volume. Problem based on mass volume. So potassium chlorate on heating. Potassium chlorate on heating decomposes to give potassium chloride and oxygen. What volume of oxygen at NTP liberated by 1 mole of potassium chlorate? So balanced equation for this change is 2Kl 2KClO3 gives 2KCl plus 3 oxygen. So mole is given for potassium chlorate. So we'll write the moles of balanced chemical equation. So 2 moles and 3 moles of oxygen. So we have to compare reactant with oxygen. So this can be excluded from the calculations. So 2 moles of potassium chlorate evolve 3 moles of oxygen. So 22.4 into 3. That will give 67.2 liters. So this is from the balanced chemical equation. This relation is from the balanced chemical equation. Now 1 mole of potassium chlorate gives 3.36 liter, and we have to calculate for 0.1. Sorry, 1 mole is equal to 67.2 by 2, and for 0.1 mole it is 3.36. So this is unitary method. For 2 moles we get from the balanced chemical equation, and for 1 mole is 67.2 by 2, and for 0.1 is 3.36. Then problems involving volume relation. Again is the same. Here is an example. What volume of oxygen at NTP is needed to cause the complete combustion of 200 ml of acetylene? Also calculate the volume of carbon dioxide form. So again, the first step is to write the balanced chemical equation. Acetylene is C2H2. On combustion means reacting with oxygen gives so hydrocarbon giving carbon dioxide and water. Then we'll balance it with trial, and on getting all the atoms of different elements balanced on both sides, we'll proceed for the solution. So calculation involving 2 ml from here. So 2 volume, 5 volume, 4 volume, and 2 volume. So 2 volume means 2 ml. Why ml? Because the quantity given in the question is in terms of ml. So we'll take volume as ml. So 2 ml, 5 ml, 4 ml. So 2 ml gives 5 ml. So 2 ml reacting with 5 ml of oxygen, right? Now 200 ml will react with 500 ml of oxygen. So this is the first part. So how much oxygen is required for the complete combustion? Now what amount of carbon dioxide is produced? So 2 ml producing 4 ml. 2 ml producing is 4 ml, and 1 ml producing 4 by 2, that is 2 ml, and for 200 ml it will be 400 ml, right? So this is all about today. So we did is percentage composition, we did empirical and molecular formula. The problems you will get in your question paper for the empirical formula involve both percentage composition and your molar concept. Then on applying these two concepts together, you will get the empirical formula. And the second is the stoichiometric problems, which are based on the chemical equations. So for solving stoichiometric equations, stoichiometric problems, you have to write first of all the balanced chemical equations, right? So bye for now. Thank you.